For the second part of our DMM basic tutorial, we'll try using it on some actual circuits. I think that'll be a good way to sort of reinforce what we talked about in part one. So here I've got constructed a simple little circuit, right? We've got our two AA batteries and I put them in series 80, and you can see I jumpered across the two middle rails. So I took the positive of the battery on the right, put it right to the negative of the battery on the left. Both batteries are pushing in the same direction. Should give me a net voltage of 3 volts approximately. Then I've got my positive side of the 3 volts coming to the lamp, to one side of the lamp, negative side of the 3 volts coming to the other side of the lamp. And I got my little lamp lit. And as you get comfortable with breadboarding, you should be able to easily see that it doesn't matter where I connect this. I could be over here. If this throws you for a loop, then think about it. I'm still on either side of the lamp, even though it doesn't look like it physically, right? But I mean, those are good things to get comfortable with, because when you're breadboarding, sometimes it's more, it's a better choice or neater to be over there, whatever. I mean, if you look at it, right, if that's still kind of messing with your head, see how those are two separate nodes and the lamp is sitting on those two nodes. So it doesn't matter where I am on that node as long as I'm on that node. You know, the red positive is on this node, and then anywhere on this node. So I can be here to turn it on, I could be here to turn it on. Here probably looks nice if you're trying to sort of get a visual on it, but it doesn't matter. So what do we want to do first? Well, we can try to reinforce some concepts. Let's see if we can go for some resistance maybe first, and because I have an idea here. So tell me what I'm doing wrong. If I switch my ohm meter on, I can see that it's ohms. It's auto scaling. It's on overload because I don't have anything connected to the leads. So it's just measuring the resistance of the air, which is very high in the megohms, and it still is too high for it to measure. Now, in this scenario, I had an idea in my head. I want to measure the resistance of that lamp. So can I just come in here with some probes and hook right onto that live circuit? Because I want to get the resistance that I see right there. And the answer is no. The thing that you're trying to measure the resistance of, it has to be isolated, and no power can be present. So power down, maybe isolate this thing. Now I can get the resistance. And I'm going to show you something that's a little tricky about even just simple lamps, but it's tricky about all kinds of resistive loads. I'll get a resistance measurement and maybe I'll jot that down. What are we seeing? Somewhere around 26 ohms. That resistance is coming from that tiny little filament inside the glass bulb. It's a real thin piece of metal, and we'll study later, of course, all the effects, but when you get a very thin piece of metal, it becomes difficult to get through. So the resistance goes up. 26 ohms, we'll call it, and let's jot that down. Okay, so I pulled the lamp out of the circuit and measured its resistance with my ohm meter. Now I want to explore some other things. Maybe I'll go over to my voltmeter setting, right? Click it over to volts DC. And kind of curious what I actually have, you know, as far as a voltage source. I know it's approximately 3 volts, but I can be more precise. So with my meter, I'm seeing 3.11. Okay. And as a technician, or you might think of yourself as a bit of a detective with your DMM here for the circuit, I mean, we can really see some interesting things if we know where to look. One thing I know to do, if you want to see something interesting, it's 3.11 approximately volts. Watch what happens if I disconnect the circuit and I stop asking the batteries to supply current. Notice how it jumps up a little bit. You know, the voltage is actually maybe 3.125. When I'm not asking it to supply current. And then when I'm asking for current, I'll get a little bit of sag in voltage, and I always will. This will always happen. And it really depends on how much current I ask for. I mean, if I asked for even more current, I would, from those batteries, for them to supply it, their voltage would drop even a little more. Because it's really just a measure of how well the chemical reaction can keep up with generating the imbalance while I'm trying to equalize it. So how well can it keep up with the current that I'm flowing out of it? How well can it keep that balance restored? So in batteries, it's really the chemical reaction. How well can it keep up with the current, maintaining the imbalance? And actually the term that you use, though, when it comes to this whole idea of a source, a voltage source, losing a little bit of its voltage ability, there's an internal source resistance, but that's a later topic. But just to let you see the things you can see with your DMM, you know, aside from just the theoretical world with pencil and paper, where you have a perfect 3 volts, but it's a little more than 3 volts. And then when you call for current, there's a little less, a little bit, you know, drops a little bit and so on. All the things you can see with your DMM, those are the real world things that are happening. And you might not be privy to them just in a pencil and paper setting. So that's the kind of thing that, you know, when you bring your tools, your test equipment into the picture, you get to try to marry up the theory world and the real world. And we'll just be doing that, you know, for the whole 2 years that you're in school. We'll just always be dancing between the two. And a good technician and a good engineering technician and a good engineer, they know how to do that. They know how to match up theory and real world, and not just take it right out of a book, but know what the other subtleties are. Okay. Well, that was one curiosity that we kind of saw with our DMM. Let's see what else we can discover. We've got the voltage on there and current, I guess. We haven't measured current yet. Now, watch out, right? I mean, here's that mistake that I mentioned in part 1. We think to ourselves, yeah, I'd like to get a look at the current. And so the mistake is, if you throw the selector switch to milliamps, you know you're going to change the lead. Hopefully you know that. This is not going to work to measure current. You've got to put it in series with the circuit. You got to insert the ammeter into the circuit. But I'll say one more thing. You have to do that before you change the selector switch, or at least at best, remember, don't change the selector switch until you've pulled the test leads off the circuit. So that'd be a good rule to make for yourself. Do you see the problem? If I throw it to milliamps first, I dead short with my 0 ohm, essentially my 0 ohm ammeter. I'll short circuit the 3 volts and blow my fuse. So I don't want to do that. So I'm going to pop these off. Now I'm a little safer, and I'm going to switch over to milliamps. Well, I think what I'll do is go all the way to the 10 amp scale. Now I know I'm not going to be anywhere that high, but I want to show you a couple things about the ammeter. Okay, tell me what I'm doing wrong here. Let's say I want to measure the current that's running through the lamp. So I've got it set for amps. I've got it 10 amps actually, and I got the 10 amp jack here. Here I go. I'm just going to poke it right across that lamp, right, to see that current that's going through that lamp. Wrong, right? I mean, that would just be a dead short again. I would have shorted out the lamp. All the current would run through my meter, and if I was on the low scale, like the milliamp scale, it would blow my fuse. So remember, you don't put the ammeter across anything. You have to open up the circuit, and it doesn't matter where, because we have a simple circuit. It's just a series circuit. Current's the same everywhere. I don't care where you open it up, but open it up. Now the current's going to flow like through that red wire, and then it's going to flow into my ammeter and back out of my ammeter and through the lamp. So I have my ammeter flowing, the circuit current flowing through my ammeter. That's what you need to do. What do you see showing up? Very small current. It's like maybe 10 milliamps, 0.01 amps or 10 milliamps. So I feel like I should change scales, right? I mean, that's not giving me the best reading. Now it's a little bit of a trade-off. I like this scale because I only am inserting 1/10 of an ohm into the circuit so that the ammeter is pretty invisible. But I'm not getting a lot of resolution as far as my measurements, so I'm going to move to the milliamp scale, knowing full well that I know I'm not going to be as invisible. I'm going to be adding 10 ohms into the circuit. I can't help it. I only paid $50 for this meter. So, and it's fine. And I don't mean to bust on the meter too much because, hey, it's a good meter for that price and it gets us through. Okay, so here we go. Now, I need to move the jack or I won't see the right measurement. So make sure you remember that. It has to be over here for 10 milliamps, for milliamps or microamps. Maybe we even saw that. Was the light? Okay, yeah, no, it was, never mind. Okay, it was still connected. All right. Aha. There's a much better story to it. Instead of just saying 0.01 amps, which was 10 milliamps, that's the best I could do. That's not really the truth, right? It's more like 15.55 milliamps. Still not totally the truth because I know I inserted 10 ohms into the circuit. So the actual current when the ammeter is not inserted would even be a little bit higher. But this is the best we can do. So I'm going to go ahead. I'm going to jot this down, what this current is. This is the current that's running, 15.55. And we don't even have to specify, you know, in this simple circuit, let's see, 15.55. I don't have to say that that's the lamp current or the current from the batteries. It's the current for everyone. There is only one current, so okay. And maybe while we're doing this, we can show it doesn't matter where you open up the circuit to look at the current. So let's show that. I could put this ammeter, I could insert it into the circuit anywhere. So I could do, let me put the circuit back intact. I could interrupt it here, you know, at the low side. And I can just reconnect the circuit then with my ammeter. Same thing, all right? If I switch the leads on my ammeter, I would just get a negative reading telling me that the current's running opposite of maybe what I think. In other words, the display again shows you the direction of current. If it's positive, it's going through the red lead to the black lead. The negative symbol here is telling me current's actually running, conventional current's running from into the black lead and out the red lead. So that's just something to keep your eye on, that negative. It won't hurt the meter. It's really just reading the polarity of the sense resistor is what it's doing. Remember, your ammeter is just a voltmeter reading the voltage across an internal sense resistor that's inside the ammeter. Okay. But if the negative symbol bugs you, but we can do it like this. So yeah, so it doesn't matter. You can just look anywhere you want. You do have to open up the circuit and put the ammeter into it again. Just keep saying that because it's deadly if you put it across anything. You're just shorting that thing out and a good chance you'll blow your fuse. So we took some nice measurements with our DMM on a live circuit. Well, not in the case of the ohm meter, of course. And that's cool. Look at some nice numbers we got. And I feel like I want to do some Ohm's law here. I mean, it just seems like that'd be the next thing to do. So let's try it, right? And see what we get. I have things like voltage and current here that I'd like to experiment with. So do you remember if you take, you remember for Ohm's law, let's see, what would it be? Voltage divided by current. That'll tell me a resistance. Maybe I can confirm the resistance measurement I made with my ohm meter, right? V over I equals R, you know, V equals IR. So I'm kind of doodling a little bit here. Bring the I over to this side. That looks good. Let's try it. Take the 3.11 volts and divide it by 15.55 milliamps. And we'll do this a lot in lab where we'll try to match theory and measurements. You know, One thing you know, if the theory matches the measurements, you know it's working right. As long as you understand everything else that could be happening, which is what we're going to demonstrate here. There's always more to learn, it seems. Now, when I do the calculated one, I feel like I must have punched something in wrong, so I do it a couple times. I keep coming up with 200 ohms. You can try it. Of course, try this whole exercise on your own. You know, put the little lamp on the 3 volts. Oh my, how am I doing? Oh, good. I wanted to turn that off. Don't want to run my batteries down. But yeah, run this. Put the batteries in series 8 in. Get your actual voltage that's happening. Power up a lamp. Get your actual current. Maybe prior to that, measure the lamp, right, with the ohm meter. Do all that. Ohm's law. And I keep checking. I must have keyed something in wrong, so let me try again. And now I'm getting a little frustrated because I keep coming up with 200 ohms, and I'm starting to think I was into this, but now I'm starting to think it's all not true. Ohm's law was just a ruse. It was just a joke. So, joke's on me. I don't believe it anymore. I see the truth. Get a plane ticket wherever Mr. Ohm resides. Drop a note on his grave. You were wrong. Okay, wait, don't buy the plane ticket just yet. What is happening here? And some of you might know. These are both right, and that might blow your mind because I know we spent all that time on the fundamentals drilling Ohm's law into your head, and now it seems like, well, which Ohm's law? They're both true. Some of you might have the answer. If we were doing this live, I would ask for your votes or your ideas. When you pulled that lamp out of the circuit, the filament inside there, that little thin metal filament, was not burning. It was cold. So this is actually the cold. It's true. It's a true resistance. But when that filament does not have current flowing through it and the metal itself is cold, the resistance is only 26 ohms. And then on the flip side, when you have it turned on and it's burning somewhat bright, that metal inside there is very hot. And we mentioned it before in passing that metal has what's called a positive temperature coefficient, which is just a fancy way of saying that when it gets hot, the resistance goes up. The higher the temperature for metal, the higher the resistance. There's more kinetic activity, and the electrons are just moving around, sort of like boiling water, and there are more collisions. It's tough for the current to flow through it because it's just so many collisions happening from sort of that kinetic energy, if you think about it, like all the electrons bouncing around. So at a physics level, that explains it. But just, you don't have to remember all that. But just remember, even from your simple lamp experiment that we did, now that we know how to use our meter, that there's a world of difference between a lamp filament when it's pulled out of the circuit and you measure its resistance versus when it's in the circuit burning bright, the filament is very hot and the resistance then is very high. So these are both true. And the 200 ohms is at play in the live circuit. So you would take these three as Ohm's law. When the lamp's burning, you have, when you apply 3.11 volts to the lamp, you'll get this current flowing, and the actual resistance is 200 ohms of the hot filament. And if you wanted to try to confirm that, you might say to yourself, well, now I'm just going to fire up my ohm meter and get back in there on that hot filament. But remember, you can't. You can't measure the hot resistance because your ohm meter can't handle a live circuit. So you are stuck with Ohm's law. That's the only way. And it kind of ties a lot of things together, I think. You know, your ohm meter can give you the cold resistance. That's not useless, by the way. We'll come back to that. Your ohm meter can give you the cold resistance. And then Ohm's law is the only way to get the actual hot resistance that's happening in the live circuit. So it kind of ties the real world and the theory world together in a nice example for you. And sometimes that's the way it is. You can only measure the voltage and the current and then calculate what the hot resistance of that filament is, but you can't measure it. So there you got a nice blend of, you know, bench type, use your meter, use your measurements, you know, and also the theory blended with it to get you the total solution, the total answer. I said the cold resistance isn't useless. It actually also is useful when you know what the cold resistance is. You actually know what the peak current of this circuit will be, because I'll tell you, when you first connect that lamp, the filament is cold for a split second, and a much higher current actually flows. Now your meter can't show that to you, but later on, when we learn how to use an oscilloscope, that's a piece of test equipment that shows you voltage in time. And so it can show you the current that happened in the first instant. And it will be very high. Well, we know what it'll be, don't we? Ohm's law, 3.11. Let me do that quick. 3.11 volts divided by 26 ohms. You'll have an initial surge current of 120 milliamps. So that's another truth to this circuit. 120 milliamp surge current will happen. Is that my meter beeping at me? 120 milliamp surge current will happen at the first instant when the lamp is connected to 3.11 volts, because it has this cold resistance. Now quickly the filament will start to heat up, and this will taper off. So it'll go from a spike of 120 milliamps and then level off to a steady state current of 15.55 milliamps. But look at the things you can start putting together. I mean, you should start really feeling like a technician, even though all we have here is 2 little AA batteries and a little lamp. Don't feel like that's not loaded with concepts that happen in bigger venues too, like we mentioned before. So this all of this still happens, even if it's not on this scale. I mean, that's why we learn it, because we use this scale to learn the concepts, but the same things happen whether it's a big furnace, you know, with an electric heating element, for example. Oh, and then I remembered that other voltage. I wanted to go back and get that. That's the no load voltage, they would call it. Remember, when we're not asking for any current, if we don't have the path, so I pulled this wire off, those batteries actually show up as maybe 3.124, even 3.125 volts. That's there. Now, I'm not asking for any current, so that's why the voltage is a little higher. And then it sags down to 3.11 when I ask for a flow of 15.55 milliamps. So again, just a nice example of getting your DMM involved in even a simple circuit. You can't get much simpler than this, right? 2 batteries, 1 lamp. But look at all the stuff you can discover. Knowing what we know from the first 2 weeks, we know Ohm's law. And then using our DMM, and then trying to put it all together, put the numbers together. And sometimes the numbers throw us for a loop. I mean, I'll say a lot of times they don't. They'll just confirm. Just that easy. Like if this was a resistor, and maybe we can do that quick instead of a lamp, it wouldn't be so tricky. That little lamp is trickier than you think. But if it was just a little 100 ohm resistor, you could absolutely predict the current. We can do that in a minute, and then measure it and confirm it, and you'd be right, and you're done. So the lamp throws a little bit of a trickery into that, where we got a little thrown here, 200 ohms compared to 26 ohms. But cold and hot resistance, very important concept. So we flushed that out. We flushed out this concept. It's just a little example to show you how much you can get out of even a simple circuit once you start understanding some of the test equipment. You have the theory behind you and the test equipment. You're turning into a technician, basically. So here I did find a 100 ohm resistor. It's brown, black, brown. That's 1, 0, 1. So the last one is the multiplier. Add another digit. We'll do more of that for you. But 100 ohms, and you can check it with your ohm meter. And in fact, if you measure it with your ohm meter, I would recommend go ahead and do that. Get your mini grabbers, pull this thing out, put your mini grabbers on it, confirm that it's 100 ohms. Maybe I'll do that real quick. We could write down the actual resistance just because it says it's a 100 ohm resistor, but then the gold band tells us that's actually a 5% tolerance, so it's plus or minus 5% of 100 ohms. So it could be anywhere between 95 and 105 ohms. So, okay, why not? Let's get our ohm meter on the case, and we'll do that quick. Okay, so I have the ohm meter, I have the resistor, the 100 ohm resistor pulled out. It's isolated. I got my mini grabber test leads on there. Looks like it's 99 ohms or thereabouts. If we slide these leads around to get rid of any oxide, see what that does. Okay, so the meter's kind of settling in. 98.9. Okay, let's jot that down. Okay, so now I have the 100 ohm resistor. Well, it's 100 ohm by the schematic, and I wrote up here, it actually turns out to be 99 ohms in actuality when we check it with the ohm meter. Before I connect the circuit back up, I just wanted to look again at my batteries when they're under a no load condition, or in other words, there's no current flowing. I have that 3.125 voltage there, and just curious now that was still there. But look, when I connect the circuit, I'll expect to see that lowered a little bit. So here I'm going to connect the 100 ohms, and sure enough, my voltage actually drops to like even lower than what it was with the lamp. But that makes sense probably because if you remember, we had a 200 ohm path, which now we have about a 100 ohm path. So the current would have gone up, would have doubled. And so we will lose even more voltage. And that's the voltage we can jot down because that's the actual working voltage when we actually have the 100 ohm path connected, well, the 99 ohm. Let's jot that down. We got 3.09 volts. Okay. And here, just for a different look, I showed you, I could be over here looking at the voltage right across that resistor. And I did that just to get you used to that because we do that a lot. Down the road, when circuits are getting more complex, if we want to have a look at current, oftentimes we'll just find a resistor that we know the value of. And if we know the voltage across the resistor, we know the current that's flowing through it because Ohm's law tells us that. So I'm looking at 3.09. It dropped a little more now. But 3.083, whatever, that voltage that's across that resistor absolutely won't lie. It tells me then the current running through it. So I don't even have to use my ammeter. And in a lot of cases, we don't. We don't want to have to insert the ammeter. It adds extra resistance into the circuit. This is a more accurate way to get current if you have a fixed resistor. Now, we couldn't do that with the lamp because that lamp's resistance changes. But with a resistor that you have a known value, absolutely, we don't have to use the ammeter. We already know the circuit current at this point. If we know the voltage across a fixed resistance, we know the current going through it. So I can adjust that a little bit. So I know the current. Just did it with the calculator. It's 31.1 milliamps. And I can kind of see that it makes sense. I have about half the resistance that I had before with the hot lamp filament. And so I would expect the current to double, right? I went from 200 ohms of hot resistance to just 99 ohms of a fixed resistor. That looks right to me, right? And at least close enough, Things are kind of a moving target. The battery's voltage can be drifting a little bit, drooping a little. And we can, of course, use our ammeter to sort of double check our calculation here. And they should agree, because there's no hot cold resistance. That fixed 100 ohm resistor has 100 ohms whether current's flowing or not through it, as long as you haven't exceeded its tolerance, its wattage rating. So I mean, it's a half watt resistor, I happen to know that, and we're nowhere near a half watt. If we start getting up into higher wattage currents, then the wattage might start heating up the resistor, and that can change its resistance a little bit. But no, basically the 100 ohm, as long as you run it well within its capabilities, it's gonna not change very much. So that we can check though with an ammeter. Now remember, we're gonna put our ammeter into the circuit. We are gonna add 10 ohms. So expect that current to change a little bit. Or maybe we don't know exactly the how much we're adding, but it's approximately maybe 10 ohms. Might be a little less. So remember how to put the ammeter in. Again, not across. You'll dead short it and blow your fuse if you try to put the ammeter to look at current. If you try to go across the resistor, like just to look at its current, that's crazy, right? Not going to do that. You got to open up the circuit. It doesn't matter where. I can just open it up here if I want to, and then reconnect the circuit with your ammeter. That's basically what you're doing. You're putting it in series. There's one way to say it. That node seems a little rough. Let's get to a different spot here. And you are putting it in series. You're basically opening but then closing it back with the ammeter. There's another way people sometimes describe it. Still in volts. Now I'm on amps. Okay, and we have the 28.24 milliamps. And if we didn't know about ammeter resistance, we might be a little dubious on that. Like, why isn't it matching what our Ohm's law is predicting? And the answer to that riddle is the added resistance from the ammeter. So, I mean, we can make a note of that. Ohm's law predicted 31.1 milliamps from our voltage and our resistor. And when we put our ammeter in to check that, we got, I can get rid of these. We got 28.25 milliamps. So we're kind of wondering, and if you're wondering which one's more accurate, the answer is this one. It's better to take a voltage measurement across a resistor and not insert the 10 ohms of the ammeter. Now, if you have a more expensive ammeter, you might not run into this problem. But you know, it can happen. It can happen even with expensive ammeters, that they can be introducing a little bit of resistance. We definitely are. And again, it reminds me of another rule for being a good technician. You have to know your equipment. You have to know what it is inside your equipment to understand things. Otherwise, you're kind of thrown here. You're not sure which one to go for, you know, which one to believe, which one's actually happening. And the answer is this one in this case. And let's even do Ohm's law with the ammeter measurement, because that'll probably rat out the resistance of the ammeter. Let's check it. So if we take the 3.08 volts that we know is there and divide it by the 28.25 milliamps that was measured by the ammeter, and I've done that here, you get a circuit resistance of 109 ohms. So voila. Looks like when we put the ammeter into the circuit, we added 10 ohms right on the nose, right? Because we had to put the ammeter in series. We had to put it into the circuit to get current measured. I mean, that's the only way you can measure current with an ammeter. Put it into the circuit. I'll get back to that thought. There's other types of ammeters, but for this ammeter, it has to go into the circuit. So we are on the milliamp scale. So we know, if we know our meter, we know that's going to add somewhere in the vicinity of 10 ohms. And we got that confirmation, you know. That's why when we took the measurement for current with the ammeter, that's why we got this current, because the circuit is now, the path is now 109 ohms. We have a 99 ohm resistor in place. It's a 100 ohm resistor, 5% tolerance, and 99 ohms is what it really is. It's just off by 1%. But we have a 99 ohm resistor, and we have a 10 ohm ammeter. Together, they make 109 ohms, which is why we read a current of 28.25 milliamps. When the ammeter is not in the circuit, we have just the 99 ohms. And in fact, we can use Ohm's law to deduce that there must be 31.1 milliamps flowing for real. And then when we try to measure it, we only measure this much because we've added 10 more ohms. Okay. Well, simple stuff, right? I mean, but good stuff for learning the basics, learning what all's involved in your test equipment, in putting the theory world and the real world together. There's a lot. And that's only with a little lamp and a little solitary resistor. And look at all the, I don't know if I want to call them issues. I mean, just I want to call them like details, I guess. They're not really issues. They're just real things that are there. And they're details that are there and understood by a technician, not even maybe on the map, not for the hobbyist. You know, you might not even be aware of all those little things going on. Might not need to be aware. But as a technician, those things can play a big role, all these little details. And they also are the fundamentals. So the thing is, when you talk about things like source resistance, which we will later on, I mean, I don't mean to throw all of these at you and expect you to just absorb it perfectly. But these are the things that'll keep coming up. So, you know, depending, and down the road, when you get a career going, depending where you're working, these are still the things that are in play. Even in the large systems that you might be working on, still kind of come down to some things like source resistance and, you know, hot resistance, cold resistance, all those kinds of things. So that's why we sort of get them out there for you to start seeing them. Definitely run these exercises for yourself. I mean, this is intended to give you the flavor of it, but it's also intended to give you good practice. So take your own lamp and see what its cold resistance measures, and then put it in a circuit, measure the voltage and current, and calculate with Ohm's law the hot resistance. Take a resistor, measure its actual resistance, you know, put it in a circuit, and so on. Do exactly the same stuff, just with a simple resistor, a simple lamp, and see if your results, I mean, you won't get the exact same numbers, but they should be similar. And that way you can get some practice. You can even get stronger on your grasp of all this. So we'll stop this video here. And of course, I think you can see where we're going with this. We're not going to stop with one resistor or one lamp. We're going to add more components. And then so we can do exercises where you have to, you know, maneuver around a more complex circuit, but that'll be coming down the road. But we'll stop this video here. It's long enough, and maybe we can do sort of some more complex circuits than in the next video.